Imagine waking up tomorrow to discover that every clock on Earth had suddenly become unreliable.
Your phone says it is 8 a.m., while your watch says 8:03, and your kitchen clock insists it is still 7:58. Satellites orbiting thousands of kilometers above your head disagree with all of them, yet spacecraft navigate billions of kilometers with precision. How is that possible? Because the universe does not measure the passage of time the way we do in our everyday lives. Most of us grow up believing that time is the most reliable thing in existence. A second feels like a second everywhere. For thousands of years, humanity shared this belief that time was like an invisible river, moving forward at the same steady pace for everyone. It was not merely common sense, it became one of the absolute foundations upon which modern science itself was built. But the universe had been quietly hiding a secret so astonishing that it would completely shatter our understanding of reality. They discovered that time is not fixed. It stretches, it slows, and it changes under extraordinary conditions. Two people can begin together, travel completely different paths, and reunite having experienced entirely different amounts of time. One person may have aged far more than the other, not because of magic, but because that is how reality works. This discovery transformed physics forever, and it all began with a simple question: what if time is not absolute? To appreciate this revolution, we must travel back more than 300 years to the ideas of Sir Isaac Newton. When Newton published his masterpiece in 1687, he gave humanity a mathematical language to describe the cosmos. His laws were astonishingly successful, but one hidden assumption would eventually bring the entire picture crashing down. Hidden inside Newton's worldview was an assumption that time flowed independently of everything else as an absolute universal clock. Whether you stood on Earth, or rode on a speeding ship, or floated among the stars, time remained perfectly synchronized. Space was simply the stage upon which matter moved, and time was the invisible metronome keeping perfect rhythm throughout the cosmos. For more than 2 centuries, this description worked so well that many scientists believed physics was nearly complete. Then, electricity entered the story as researchers uncovered an unexpected relationship between electricity and magnetism. In the 1860s, James Clerk Maxwell combined these discoveries into 4 elegant equations, predicting that light was an electromagnetic wave. Those equations predicted that these waves travel at around 300,000 kilometers every single second, the speed of light. But this raised a massive puzzle compared to what exactly did light travel at this absolute speed limit. Imagine sitting inside a train, moving fast and throwing a ball forward. Ordinary experience says speeds simply add together. Yet Maxwell's equations predicted one speed, always the same, no matter who measured it, causing a massive contradiction. Scientists searched desperately, believing light must travel through an invisible medium filling space called the luminiferous ethers. In 1887, Albert Michelson and Edward Morley built a sensitive instrument to measure Earth's motion through this mysterious ether. They repeated the experiment during different seasons as Earth moved in its orbit, but the result never changed, showing no evidence of an ethero. Light refused to behave as classical physics expected, threatening everything physicists believed about reality. Then a young patent clerk in Switzerland looked at the problem differently, and the next idea would redefine time itself. What if the experiments were completely right, and our foundational understanding of time itself was fundamentally wrong?
The year was 1905, and Albert Einstein was only 26 years old, working as an outsider to the scientific establishment.
Instead of changing the experiments to fit the old theories, he chose a different path and changed the theory to fit reality. Imagine chasing a beam of light inside a spacecraft, accelerating faster and faster until you almost reach the absolute cosmic speed limit. In 1905, he published the special theory of relativity, resting on just 2 deceptively simple principles. The first was that the laws of physics are identical for every observer moving at a constant speed with no preferred frame of motion. The second principle was that the speed of light in a vacuum is always exactly the same, regardless of how fast the source moves. If the speed of light never changes, then something else must change. Distance and time cannot both remain fixed. To understand why, picture a simple clock made of 2 parallel mirrors facing each other with a light pulse bouncing endlessly between them. Now imagine watching that light clock fly past Earth inside a spacecraft, traveling at an incredible velocity. From your stationary perspective, the light can no longer travel straight up and down. Instead, it traces a long zigzag path through space. Because the distance is longer while the speed remains identical, each tick must take more time, meaning the moving clock runs slower. This is time dilation. It is not caused by broken mechanical gears. Time itself is flowing differently due to motion. This sounds impossible because human intuition evolved in a world where everyday speeds are tiny compared to light. But as you approach 99% of light speed, the effects of the Lorentz factor become completely impossible to ignore. The speed of light is not merely fast. It is woven into the very structure of reality, acting as the ultimate speed limit of the cosmos. Einstein uncovered that space and time were never separate. They are part of a single interconnected fabric we call space-time. Each observer carries their own clock through space-time, experiencing reality along their own unique relative path. High above Earth, tiny visitors from space were already carrying the evidence. Nature had been performing Einstein's experiment for billions of years.
If Einstein's theory was correct, then time should behave differently for objects moving at extremely high velocities.
Consider the muon, an unstable subatomic particle that survives for only about 2.2 millionths of a second before decaying. Simple calculations based on Newtonian physics predict that almost zero muons should ever survive the journey to the ground. Yet sophisticated detectors placed at sea level observe enormous numbers of these particles arriving every single day. Because they move near light speed, their internal clock ticks slower, allowing them to complete a journey that should be impossible. To the muon, the distance to Earth's surface becomes dramatically shorter, an effect known to physics as length contraction. Eventually, humanity learned how to build massive machines capable of recreating these extreme conditions, called particle accelerators. Inside facilities such as CERN, electromagnetic fields accelerate particles until they travel over 99% of light speed. The faster they travel, the more slowly time passes for them, confirming that time dilation is a fundamental law of nature. Yet one famous question continued to trouble people: if motion is relative, why does one traveler age less than another? The key lies in acceleration. The astronaut must turn around and reverse direction, breaking the symmetry between the twins. Each person follows their own path through space-time, accumulating different amounts of time along their unique journey. You can travel into the future simply by moving fast enough, as every astronaut orbiting Earth has already experienced. But speed is only half of the story. Another force can slow time even more dramatically: gravity.
By the 1960s, Einstein's theory had survived every challenge. But could time dilation be measured with ordinary clocks?
In 1971, Joseph Hafele and Richard Keating placed 4 atomic clocks aboard commercial airliners, and the results would prove that time itself could be measured changing. When the aircraft landed, the clocks differed from those left behind in the direction and scale predicted by relativity. Today, modern optical atomic clocks are so precise that moving one by just a few centimeters in height produces measurable changes. And nowhere is that more important than in the navigation device sitting directly in your pocket, your smartphone. Because gravity is weaker in orbit, satellite clocks run faster by about 45 microseconds every day. If engineers ignored relativity, GPS errors would accumulate by nearly 10 kilometers every day, making the system useless. Every successful journey guided by satellite navigation is another confirmation that time does not flow equally everywhere. The closer you move toward the speed of light, the more dramatically your personal timeline stretches out compared to Earth. One question continued to haunt Einstein: if motion can slow the passage of time, could gravity do the exact same thing? And general relativity would reveal that the universe can sculpt time into shapes more bizarre than anyone had ever imagined. Time may be a dimension that bends, stretches, and slows, connecting every atom since the birth of the cosmos. And every answer reveals a deeper mystery beyond it.